Okay, let's talk numbers now. If I use an automated low-flow anesthesia machine to reduce agent use, yet will increase absorbent use, where do I end up? At this time, there are only two target-controlled low-flow anesthesia machines. One is the Zeus, which uses automated closed circuit. The other one is automated minimal flow. The ACES in target control uses 500 milliliters per minute. We're going to have a look at agent usage, how to model it, absorber usage, look at the combined cost, and make some final reflections. How low can you go? If I'm using 2% sevoflurane or 6% desflurane and expires. That's a number I'm going to use throughout the lecture. And I'm giving anesthesia for 1 hour. I'm using oxygen A. That's the lowest you can go. This is a work Andre and I did many years ago. What we did was we used a closed circuit anesthetic and we injected the liquids. So we measured the actual liquid that we used in the closed circuit. You can't go any lower than this. So for these settings you get 13 milliliters of DES, 6.5 milliliters of SIVO, liquid. That's the lowest you can go. Here's the references. Most of it is taken by the patient. Small amount is used to prime the circuit with lungs. Automated low flow will never be able to reduce consumption at 1 mAc in an adult below these numbers. What does the ZEUS do? These are data we presented in Barcelona a few months ago. These are data we'll be presenting 2 weeks from now in San Francisco. So we used the ZEUS at the ASA meeting. So the ZEUS uses 14.2 milliliters and 6 milliliters of SIVO. I was still at a learning curve here. We had a hard time measuring the usage during the first minute because of technical issues. Anyhow, the system, we measured we placed a balloon on the exhaust of the ZEUS and we measured how much anesthetic came out, and it was basically nothing, 0.08 to 0.19 milliliters. So I'd say this is closed. Now what about the ZEUS? Here's some data we'll be presenting 2 weeks again in San Francisco, and some new data. So not peer-reviewed these. So that's where the ACES in target control ends up. So this is closed circuit. This is minimal flow anesthesia, 500 milliliters. So you can see there's a difference. Why is there a difference? First, the ZEUS allows more time to reach the target FiO2. So what we have here, we have time. These are the ZEUS data. The ZEUS controls, or the target for the oxygen you set for the ZEUS is the inspired oxygen concentration. ACES has chosen to use the end-tidal concentration. You can see if you start and you enter your target, the ZEUS will take its time to get to the target FiO2. The ACES thinks it's very important to rapidly reach the target, so you'll get rapidly your target. But there is a price to pay for this. You have to look at the fresh gas flow the two machines are using. This is the ZEUS. And look at this line here. So that's the fresh gas flow that the ZEUS is using. And now we have to look at the first 5 minutes here. So that's around less than 180 milliliters per minute. So basically closed, because oxygen consumption by an adult is approximately 180 milliliters. The ACES uses a high fresh gas flow, or has to use a high fresh gas flow, because it likes to go to the target fast. So that's but obviously this comes at the expense of increased agent usage. And it'll become clear if I scale this is 500 milliliters, this is 2,500. We're putting it on the same scale, so you can see this is where the ZEUS is working. And the ACES uses a high fresh gas flow initially. Actually, the ZEUS was doing exactly the same thing when it initially came out. And we actually found that the ZEUS, with the first software, used more than when you used a conventional anesthesia machine in a certain manner. They've adjusted the software, and that's how I think they got to the results I just showed you a few minutes ago. Second thing, of course, is that the maintenance fresh gas flow with the ZEUS is lower. This is minimal flow anesthesia. This is closed circuit, so really uptake. Again, 200 milliliters is the oxygen production, the oxygen consumption by our patients. Now, if we have these numbers, we can multiply them by the cost, and we get total agent costs. So number one's done. We've modeled the agent usage. Now we have to model absorber usage. Let's assume, again, first let's have a look at canister usage with the ACEs. Ventilation 5 liters per minute, CO2 production 160 milliliters. Let's take our first canisters. We're going to use a fresh gas flow of 0.2 liters per minute. Canister 1. Here we go. Suddenly the canister becomes exhausted. The FiCO2 rises. My cutoff value is 0.5%. So I replace the canister when the FiCO2 is 0.5%. And I'm going to recalculate a bit because it'll allow me to do some cost comparisons. If it takes 10 hours to get to an FiCO2 of 0.5%, then I basically use one canister per 10 hours, or 1/10 of a canister. So I use 10% of canister A per hour with a 2.2 liter per minute fresh gas flow. Now let's have a look at, I'm going to do another experiment here. Same thing, same machine, but different fresh gas flow. New canister. Obviously, because the fresh gas flow is higher, it will last longer. For example, 25 hours. So if the canister lasts 25 hours, then that means that I'm using 1/25 or 4% of canister B per hour. I'm going to plot these data on a graph. And this is the fresh gas flow I've been using. This is the percentage of the canister I used. Remember, canister A, fresh gas flow was 0.2 liters per minute. I used 10% per hour. Fresh gas flow of 3 liters per minute, different canister. Lasted 20 hours, so I used 4% per hour. Now, and these are the data for other fresh gas flows, and it's interesting to note, and I actually was a bit lucky, I must say, in retrospect, that with the ACEs, all the dots fall on the same line. I want to say that when I did the test for the canisters, I used canisters of the same lot. They were all exactly the same lot numbers. So they should have had the same composition. So they fall on a straight line, so that made it easier for me because I could just draw a straight line through it. And if I know the intercept here, and I know the slope, actually, then I can calculate canister usage. And if the line goes through 5, why? Because 5 liters per minute, that's where you have no rebreathing. So the canister should last forever. So we have this, I can calculate it. We got this, it took me 3 years to get to this, and a lot of patients of Dr. Lust. Yeah. I'm sharing an office with Dr. Lust, and he had a hard time getting into the office we are sharing because the room was just packed with canisters. So thank you, Wouter. I couldn't have done the study without him. Thank you. So these are the numbers. If you have these numbers, you can actually calculate the canister uses per hour, fresh gas flow times the slope times the intercepts. These are the data for the different canisters when you replace it at 0.1, 0.5. If I then multiply it with the cost of the canister, I get cost per hour. I just multiply it. So the cost of one canister times how much you use in percentage-wise gives you the cost of the canister per hour. Okay, so we've gotten these. First I'm going to show you the data if you use 0.1% as cutoff value to replace the canister. So these are the regression lines. They all had R squares of 0.98. I mean, it was a straight line. So this is the Medisorb canister. This is the Spherosorb and Medisorb. Remember, these contain a little bit less sodium hydroxide, but it comes at a price. They don't last as long. So the higher they are, the more you use, the shorter the canister life. Here we have the low flow sorb and the M-sorb. And here's the Eclipse. So again, this is all calcium hydroxide. This is lithium hydroxide. This threshold is 0.1%. And obviously, if I wait a little bit longer and I use 0.5% as a threshold, this is where I end up with. So 0.1, you use more. 0.5, you use less. And you also will notice that the relative position of the different absorbers changes. So we've now put a price on it. Let's say I pay 20 euros for all canisters, all the same price. That's where I end up. So if I use a totally closed circuit, I end up with these price ranges under these conditions with a patient producing 160 milliliters per CO2 with the ACEs anesthesia machine. Always keep in the back of your mind these boundaries that we set. Again, this one has to be tested differently. These are all the data with the ACEs. So now I know how much the ACEs uses agent-wise during closed circuit. I know how much each of these absorbers I use with the ACEs. Now let's look at the Zeus. Again, I want to reiterate, it's difficult to directly compare canister usage of the Zeus with the ACEs because they have a different rebreathing pattern. And probably the Zeus, because of the fact that there's a continuous high flow into the circuit, kind of gets rid of the temperature gradient in the canister, which affects performance. So don't compare them directly. Here are I'm not going to bother with you, but here's the y-intercept and the slope, so the parameters you need to derive the graphs. So now let's add it up. We have agent usage, absorber usage. I will use some numbers in the upcoming slides. Do not apply to your situation unless you're absolutely sure that you figured in all the details. Contact individual companies for details. You're welcome to contact me to get some data, but I will make no cost comparisons or interpretations of specific situations. I have no conflict of interest. Again, we're looking at this. These are the boundaries. I'm giving you a Belgium example. Costs differ between countries. Reimbursement systems differ. This is in this very specific setting in Belgium with these machines and these numbers I put on there. 1 hour anesthetic, 2% SIVO. This is the cost of the SIVO. This is the 6% desflurane, cost of the DES liquid. And I just put a price on there, 20 euros. It can be 15, whatever. I want to get the concept across. These are the numbers we got before. Target control, low flow anesthesia. That's the title of the symposium. So that's the usage with the ACEs and with the ZEAs of the desflurane and sevoflurane. So now let's get it into costs. Here is cost in euro. This is, we're looking at the ACEs now. The ACEs uses a 0.5 liter per minute fresh gas flow. This is the cost of the canisters. This is the cost of the sevoflurane. And this is the total cost for each of these different canisters. Okay, Medisorb, etc. All the same price. So we end up with 6 euros total cost, approximately. Desflurane, obviously the canister cost will be the same. Desflurane cost actually is here. So we end up with a total cost of around 9 euros of 1 hour. What does the Zeus do? Here are the data for the Zeus. I'm going to plot them in a similar manner as actually I'm going to put them together right here. So here we can do a direct comparison again for Belgian situation, this hospital within the constraints that I pointed out for sevoflurane with the ACEs and the Zeus with different canisters. You end up with this canister cost, the sevoflurane cost, and the total cost. So 6 euros with the ACEs, 4 euros with the Zeus. Desflurane, end up with about 9 euros with the total cost with the ACEs and around 6.5 euros with the Zeus. So ACEs, Zeus, the figure speaks for itself. These are small differences, but this is where automated low-flow anesthesia will lead us. But let's put everything in a broader perspective again. Remember, most of us intuitively use a 2 liter per minute per fresh gas flow. If you look worldwide, most people use a 2 liter per minute fresh gas flow. Why is that? If once you start to go lower than 2 liters per minute, there is a discrepancy that develops between what you dial and what the patient inspires. And intuitively, all of us go with a 1.5 to 2 liters per minute fresh gas flow. You find these numbers over and over again in the literature. So it's again important to put that in a broader perspective. So let's see what the ACEs does to that regard, with regard to cost. Most of us are working here. Well, if you use the target control ACEs, it'll just bring down the cost. I mean, if you put it in percentages dramatically from 9.5 euro to 6 euro, that's quite a cut. So getting a target control automated low flow anesthesia machine will decrease the total cost of your sevoflurane and canister significantly. Interesting with the current cost settings here, and again I want to point out that these settings are very important. They may differ from place to place. It's interesting to note that the cost doesn't decrease that much below here. So it's a great job bringing us down from 2 to 1 liter per minute. Minimal cost savings below there. And again, I want to warn that this is one particular situation. Different countries have different cost structures and different reimbursement schedules. So is it worthwhile buying a new anesthesia machine to cut back on the costs? It's very complex. You need to take into account the fresh gas flow you're working with now. Inpatients and outpatients get different reimbursements. It depends on the canister you're using. It depends on who's paying for what. And then it depends on the difference in cost between the old and the new anesthesia machine. And it's pretty complex to figure it out. But I think we have the data. If you want to do the calculus for yourself, I think this may help you doing some calculations for yourself. We're thinking about, I'm going to modify this, but we're certainly going to have the data available to, because these are non-peer-reviewed data. I want to make sure there's no errors in there. So I'm going to look over the data with the interested parties. We'll see about how publicly available we make the data, but certainly with the individual manufacturers, you're welcome to have a look at the raw data to make sure that they match what you find, because I don't want to take the credit for making the errors for items that are so important to you. So we have to double check. So to that, again, the data I showed you are preliminary, non-peer-reviewed data that are sitting in my laptop. Okay, but we've been presenting them at the ESA, and we will be presenting them at the ESA next week. Again, putting it in perspective, if we're talking about 4 euros, 6 euros, 10 euros. If a surgeon drops a disposable stapler on the floor, it costs $1,000 or 1,000 euros. My models do not take into account the effect of carrier gas composition. If you use nitrous oxide, it changes things quite a bit. It's pretty complex, actually. If you make frequent target changes of your carrier gas or your inhaled agent, it'll have an effect on usage. Obviously, if you don't hit the start automated low flow button, what good are you having a low flow anesthesia machine? So the question remains now, these are all models, but the question remains, what happens when you actually get an automated low flow anesthesia machine in the operating room? So I'm going to ask Philip Payton, what was the effect of introducing the ACEs in Australia? And Phil has been looking at this just very recently. Okay.